this whole chapter, both chapters 8 and 9, this whole unit is about solving systems and using them to solve problems. You're going to find different ways to solve them. Maybe up on the back of the title page. We should use this as a kind of important notes from the whole chapter. A system is two, or I'm going to put or more. We're not going to do or more in this year, but two or more equations we'll put with common variables. And considered together, taken together. And we'll put our example there. We had y equals, what if we had y equals 3x and x minus y equals 8? Now let's change that around. Let's make it y minus x to make it easy. Okay, it doesn't matter what you put there as a system, but anybody see what the solution is to that just by playing around with numbers in your head? If one number is 3 times the other, and they subtract to 8. Anybody see what the solution would be? What pair of numbers? Any ideas? Well, there's different ways you're going to find, because even here, this is not that difficult of a one number-wise, but it's not obvious what the solution is right away. We're going to solve systems a bunch of different ways. Ways to solve systems. Find sets of numbers that work in both. Now I'm saying both, but you could have more than 2 equations. No, we're not doing that this year. For this year, we can just say 2 equations with common variables, but you might work with systems of 3 equations or whatever, right? But what we're doing, we're just doing 2, so that's why I'm saying both here. But obviously, if you had more than 2 equations, you have to work in all of them, but we don't want to make it too complicated. So I put sets of numbers, but for us, it's going to be pairs of numbers because we're only going to have 2 variables. So we're looking for pairs of numbers. And we're only working with straight lines too. So here's ways to solve it. One way would be to just try and look at the thing and figure it out. Guess and test. Is that a good way to do it? It's a way to do it, but it's probably not very efficient unless you happen to see what it is, right? The first thing we did there was make a table. Make 2 tables. Okay, I'm going to put not great. Not a great method. Not great. If you're using a spreadsheet or something, you could look for it, but it's not the greatest way. What was the other way that we hinted at there with that activity? What's the other way you could do it? Make 2 tables. Try numbers. Graph. Create a graph and look for the intersection point. Especially if you have technology, that's a pretty good way to do something. It's visual. You can see it. Graph. Both. Find intersection. Okay, so those are what you look at in the first. This one right here is section 1 here. Okay, section 1 you're looking at solving by graphing. Some other ways that you learn in here, you learn algebraically. This one where you're creating tables of numbers, that's kind of solving it numerically, making tables and just looking at the pairs of numbers. This is solving it graphically with a graph. There's different ways of solving it algebraically, which we're going to get to here. You're going to solve it algebraically by substitution. And you're also going to learn to do it algebraically by what we're calling here elimination. Or what sometimes you see on, in some books or on the internet or whatever. Let's put AKA, or multiplication addition. That's what they often call it. Okay, so here's the 3 big ones, right? That one, and that one. Sections 1, 2, and 3, you're looking at that. Okay, this is section 2. This is section 3. You also have to look at a concept that's fairly straightforward if you realize that all we're dealing with is straight lines. Other things to know. Here's some other things to know in this unit. How many solutions might there be? How many solutions were there to that system that I gave you? How many pairs of numbers were there? There was one pair, right? One pair of numbers. From the graph you can tell, are there going to be any other pairs of numbers? Ever? Never ever, right? Because this line goes like that. It doesn't curve. And this line goes like this. It doesn't ever curve. There's going to be one pair of numbers for that. Can you envision any other situation where there's a different number of solutions other than one pair of numbers? How could you have two lines so that there's something other than one solution, one place they cross? If you have something like this and something like this, one solution. Right there, right? What else might you have? Is there a way you could have no solution? Can you have a situation where you have no solution? How could you have no solution? What if you happen to have a line like that and a line? How could you have it so there's no solution? If they're parallel, right? If you have two lines that are exactly parallel, I think that's pretty close to parallel. Let's pretend that that's parallel. You know the symbol for parallel is this little arrows on there. There's no solution, right? No intersection. You can have no solution. Or there's one other situation you could have. If you have two equations, but they actually turn out to be, what if you have one line right here, and then you go to graph the other line, and it happens to be right on top of the other one? What about that? How many solutions are there to that situation? A lot? How many? Infinite number of solutions? Infinite number of solutions. Those are the only things that can happen. You can have one solution, no solutions, or infinite number of solutions. These are our only situations that we can have. This is actually section 4 in here. It's really short. Number of solutions. That's basically it. You have intersecting lines. You have parallel lines. Or does anybody know what the word would be for this? Lines that are on top of each other? They're called coincident lines. What does the word coincidence mean? If something is a coincidence, what does the word coincidence literally mean? Coincidence? Coincide? Coincidence means two things happening together, right? If you have coincident lines, they're on top of each other. On top of each other. That would be basically if I was giving you the same condition twice. The last two sections are solving problems, okay? Representing situations and solving problems. Representing situations is section 5. Solving problems is section 6. Representing situations, you've had a lot of background in this in grade 8 and 9. You know the situation just we had here? We'll use the example. 2 numbers add to 10. Add to 10. One number is 4 times the other. Let's stick with the words here. Okay, this situation is just going to be represented with a system. There's two conditions here, right? 2 numbers add to 10. How did we write that before? X plus y is 10. We're going to be very good students and say things like let x and y be the numbers. Right? Use a let statement. But this is what you're going to get to in the second last section here. And then the other condition is one number is 4 times the other. How did we represent that before? One number is 4 times the other. Y equals 4x. This is a system. In grade 8 and 9, you solved problems by using one equation with one unknown. Now you're solving problems that have two equations, or that have two unknowns. You're using two equations. Okay, if you solve that together by one of the methods, you come up with an answer and you're all good. That is this chapter. It's all focused on the same thing. It's not a bunch of little bits and pieces. First thing you do is find 3 different ways to solve systems. Graphing, 2 different algebraic ways. And then fourth thing is, how many solutions might there be? That's pretty quick. And then last thing is solving problems.